what is the next step? The next step is to determine the output voltage and input current. That is what we are interested in. So the process has been the same. We first identify the states that are possible, switch states that are possible, and then we would like to look at the variables of interest, the quantities of interest. What are the quantities of interest to us? We want to know whether the output voltage is a pure DC or how close it is to the pure DC or not. And we want to know how close is the input current to a sinusoid. Let us look at the output voltage first. We have concluded that one from top group, one diode from top group and one diode from bottom group always conducts. Let us say we take the state D6, D1. So when D6 and D1 are conducting, D6 is conducting and D1 is also conducting. What will be the output voltage? The output voltage will be, see, R is connected to this point X1 and Y is connected to X2. So the output voltage will be VRY. VRY. And if you take the state D1 on and D2 on, what will be the output voltage? It will be VRB, because now B is tied to the point X2. Let us take another example. Let us consider the case where D3 from top group is conducting, D4 from bottom group is conducting. When D3 is conducting, X1 becomes Y, and since D4 is also conducting, X2 becomes R. So the output voltage is VYR. What do we observe? The output voltage, that is the voltage across X1 and X2, will always be the line to line voltage. It means it is either VRY or RB or YB, BR, BY, all possible combinations of line to line voltage. That is the voltages among all these 3 points R, Y, B appear at X1 and X2. That is why we have shown all the possible combinations of line to line voltages plotted in the second set of plots in this figure. So when D6, D1 are conducting, the voltage is VRY. That is this. And when D1, D2 are conducting, it is VRB. When D2, D3 are conducting, it is VYB, and so on. So the output voltage, which is shown in purple color waveform, has sections from each line to line voltage, and there will be 6 such sections because the output voltage will follow a different sinusoid every 60-degree interval, because 2 diodes can conduct together in a 60-degree interval. And it is also worth to note that for a resistive load, this purple color waveform is the voltage across a resistor as well, and for an inductive load, like when you have an L filter with R load, this waveform is VO dash. And how do we calculate the average value of this waveform? The average value of output voltage waveform can be found by integrating this section. That itself will give us the required average voltage. We shall see what that integral is and what is the value of that integral. And what is the maximum value of output voltage? It is √3 times Vm. That is important to note. Vm is the peak of phase voltage. Since the output voltage contains pulses from line to line voltage, maximum value of output voltage is the maximum of line to line voltage, which is √3 times the phase voltage. And what is the minimum value of output voltage in the case of a resistive load? In the case of resistive load, the minimum value of output voltage will be √3 by 2 times √3 Vm, and that is what is this 1.5 Vm. So it is again from the 30 degrees angle. And what else we are interested in apart from output voltage, we are interested in the input current, the current drawn from each sinusoidal source. And how do we get that current? That current can be obtained by looking at the diode currents. See, for example, IR is ID1 minus ID4 because of KCL. So we need to look at the diode currents D1 and D4, and we know that D1 and D4 conduct only for 120 degrees in a line cycle. So from 30 to 150 D1 conducts and it will be off for the remaining duration. Similarly, from 210 degrees to 330 degrees D4 conducts. It is also worth noting that D4 starts conducting right 180 degrees after the starting instant of the conduction of diode D1. So D1 has started conducting at 30 degrees. So D4 will start conducting 180 degrees later, that is at 210 degrees. And of course it will stay conducting for another 120 degrees, that is up to 330. Similar observations can be made for the pairs D2 and D5. See, D2 starts conducting at 90 degrees and D5 starts conducting at 270 degrees, that is 180 degrees later. D3 starts conducting at 150 degrees and D6 starts conducting at 330 degrees, 180 degrees later. And how does the current vary when a diode is conducted? Since only R is connected between X1 and X2, that is only R load is being considered, the current is proportional to the voltage. That means whenever D1 is conducting, the current waveform will be proportional to this section, because it is just this divided by R, this voltage divided by R, and that is what is shown here. Similarly, when D4 is conducting, its current will be the output voltage divided by R, and that is what is shown here. Source current is ID1 minus ID4. So ID4 gets flipped on the source side and ID1 appears as it is. So we have positive and negative excursions in the source current waveform, that is waveform of current IR, the current drawn from R phase voltage source. Similar currents will be drawn from Y phase and B phase also, and the currents will also be shifted by 120 degrees. That can be observed. And what is the peak value of the source current? It is root 3 Vm by R, because the peak value of voltage is root 3 Vm. The interesting point to note here is that the source current IR is 0 for 120 degrees in a line cycle. Why? Because neither D1 nor D4 conducts in these intervals. Let us consider the case of L filter plus R load now. When an L filter is added, the current waveform follows exponential plus sinusoid, as we have already seen in the case of 1 pulse and 2 pulse diode rectifiers. What is the sinusoid that is appearing across this LR circuit? The sinusoid here is this section of line to line voltage. So one particular section of line to line voltage appears across this RL circuit every time. If you start with 0 initial condition, the current rises and then it will continue to rise and it will reach a steady state, as we have discussed earlier in the case of single phase rectifier. We have drawn waveforms in periodic steady state. So considering periodic steady state, the current will follow a solution of, I am drawing the current IL, output current, sinusoidal plus exponential, it will have a solution something like this. and the same current is flowing through D6 D1 in this interval, D6 D1. So D1 will have same waveform, and D1 will also have same waveform for 60 degrees more, and then it will be taken over by other set of diodes. The same current waveform IL will be equal to the current flowing through D4 in these intervals. So negative of that will appear here. So the source current will appear something like this, will look like the last blue color waveform that I have shown for an RL load. This is the current waveform for an L filter with R load.